These slides are the first in a series on coastal depositional environments. We're going to spend the next 2 weeks or so discussing a variety of environments from deltas, estuaries, tidal flats, barrier islands, but we're going to start with open, wave-dominated coasts because they have the simplest spatial distribution of facies. So this video is going to introduce some new sedimentary structures that we haven't encountered before and discuss their distribution across the shallow marine shelf. I'll also introduce one of these sequence stratigraphic surfaces, the regressive surface of marine erosion, which is basically only found in these coastal environments. In the open ocean, when the water depth is deep, water moves by waves in purely a circular motion. But when the water becomes shallower, the waves start to interact with the seafloor, and the wave orbitals become squished. Right by the seafloor, the water motion becomes just a back and forth oscillation. So waves begin to interact with the seafloor when the water depth is less than half of the wavelength. And this is something called wave base. This depth is what's called wave base. Typical fair weather normal waves have wavelengths on the order of 10 to 30 meters. So this means that they interact with the seafloor when the water depth is around 5 to 15 meters. That depth is what we call fair weather wave base. Storm waves, on the other hand, can have much larger wavelengths, up to maybe 400 meters in rare cases like really big hurricanes. So they affect much deeper parts of the seafloor, maybe anywhere between 30 to 125 meters depth. So that depth where storms actually start affecting the bottom is called storm wave base. Of course, wave energy in any environment is a continuum. There aren't really distinct fair weather and storm wave bases, but the concepts are still useful nevertheless. We can use these concepts of fair weather wave base and storm wave base to subdivide the shallow marine shelf, or the littoral zone, into environments. These environments are called the beach, which is everything above the mean low water point, or the mean low tide. The shore face is the area between the mean low water and the top of fair weather wave base. The offshore transition is everything below fair weather wave base, but above storm wave base. And finally, the offshore environment is below even storm wave base. So considering the offshore environment, and this holds for any depositional environment, grain size is a function of energy levels and proximity to the source. Because the offshore environment is below storm wave base, the energy levels are very low. And because it's far from the coastline, it's very far from the rivers that supply sediment. So as a result, the sediments are fine-grained, often mudstone or siltstone. There may be occasional very thin sand beds. These are called tempestites. They're distal or far-away flows from storms. This photo here shows some typical fine-grained offshore facies, particularly in the bottom part of the section. The area around the arrow is potentially offshore transition, but the fine-grained, thin-bedded facies at the bottom are very typical of the offshore. If we move above storm wave base, we start to see some higher energy features. And energy levels are intermittently higher during these storm events, and these long wavelength storm waves generate a distinctive sedimentary structure, at least in fine or medium sand, called Hummocky Cross Stratification, often abbreviated as HCS. HCS appears as these large, broad domes or hummocks. They can be up to a couple meters across, but they're typically maybe 1 to 2 meters across, and they're a few tens of centimeters high. Inside them, they have gently curved laminations, which are convex up in the hummocks. There are also concave up laminations called swales that are between the hummocks. Because these offshore transition environments are characterized by high-energy storms that are fairly intermittent, punctuating more continuous low-energy background conditions, the facies often have interbedded sandstone with HCS representing the high-energy storms, and mudstone or other sort of fine-grained sediments representing the background time. The base of the HCS sandstone beds is potentially erosive, with sole mark features like gutter casts, these scoured grooves on the base that come from turbulent scouring by storms. So in the offshore transition, The characteristic facies and sedimentary structures are interbedded sandstones with finer grained sediments, and the sandstone beds often have HCS being a very distinctive feature of the offshore transition. Those sandstone beds will have will have sharp bases, potentially with scours like gutter casts. If we move above fair weather wave base into the shore face, in the shore face environment, there is fairly continuous wave energy. So this means that the mudstone interbeds disappear or become very rare. Wave energy here, even from fair weather waves, is sufficiently high to keep mud in suspension so it is not able to be deposited. We'll talk about a couple different types of shore face environments. The first one is if the shelf or in the shore face are storm dominated. If that's the case, the HCS may transition upwards up section into a related sedimentary structure called Swaley Cross-Stratification, or SCS. So in SCS, the hummocks, the convex up domes, are rare or absent, and so it's dominated instead by these large, low-angle scooped swales, which give Swaley Cross-Stratification its name. So SCS is a pretty diagnostic feature of storm-influenced shore face zones. If the large storms are not very common, the shore face will instead be dominated by wave ripples just from fair weather wave action. You've learned about the current ripples before in the fluvial lectures, so how do wave ripples differ? Well, in their overall shape, wave ripples have a symmetrical or fairly symmetrical cross-section, in contrast to the asymmetrical stoss and lee sides that you saw in current ripples. There's actually two different types of wave ripples formed by different processes. We're not going to worry about that detail, but a lot of wave ripples have a sharp crest, which can branch in these Y-shaped or tuning fork bifurcations, like the arrow on the right-hand picture. Wave-generated flow isn't always perfectly bidirectional. It may favor one direction or over the other, so wave ripples can contain dipping laminations or cross-laminations within them. They do dip, I think, at lower angles than fluvial cross-stratification generally. But even then, the ripple is fairly symmetrical in cross-section, and as you see in the ripples in the layer next to the quarter, it may also have continuous layers draping symmetrically over this crest. True bidirectional flow should produce these sort of tent-shaped or upside-down V-shaped chevron laminae. The layer just above the quarter has some more irregular laminations dipping in a variety of directions, more typical of wave ripples. There's one final type of shore face to consider. It's probably not very common, but it does occur, and this is a shore face in which longshore current energy dominates. If the waves hit the shoreline at an angle, the shore parallel component of energy creates a current flowing continuously along or perpendicular to the shoreline. And if that current is strong enough, and if storms are weak or absent, the shore face sediments can be dominated by large dunes that are migrating along shore, and so they produce large, likely planar crossbeds that have a paleocurrent direction perpendicular to the shoreline. So this slide just summarizes the typical sedimentary structures in different types of shore faces. Remember that shore face will be nearly entirely sandstone, with very little, if any, mud or silt because of the near constant wave or longshore current energy. So finally, the shallowest or the most proximal environment in the coastal zone is the beach environment. This is the area above the average low tide position, above the mean low water. It includes the foreshore, which is the area between low and high tide, where wave action is relatively or nearly continuous. And it also includes the backshore, which receives sediment probably only during large storm events. So foreshore sediments dominate beach deposits in the rock record. And they're dominated by wave swash, the waves rushing up the beach, then gradually flowing back down the beach slope. The wave swash, some of them marked by the red arrows there, it has fast velocity, it has a very shallow flow depth, and also because beaches typically have very well-sorted, mature, fine sand grains, all those three features, as you've learned from the unidirectional bed form phase diagram, tell you that you would expect to find upper plain bed in this section. So therefore, thin parallel laminations, likely with parting lineations on the surface. Here's an example of typical beach deposits. But even if the parting lineations aren't visible, the planar lamination, the very mature sand, and really importantly, the fact that the foreshore actually dips at a low angle is very indicative. So the beach dips at a couple degrees, maybe up to 5 degrees relative to the bedding of the environment. And so as a result, this low angle seaward dipping stratification is a very strong indicator of beach deposits. There can also be shallow scour surfaces that erode little grooves or troughs within this otherwise planar lamination. Well, as you know from our Pebble Beach field trip, not all beaches are sandy, of course. And as you know from the fluvial lecture, upper plain bed only forms when the grain size is fine sand or smaller. So you, of course, won't see parting lineations in a gravelly beach. But the presence of this low-angle, seaward-dipping planar layers, possibly with small scours, is again going to be a really good tip-off that this is a beach environment or a foreshore environment. So here's a recap of all the sedimentary structures and their distribution across wave-dominated coastlines. So in class, you're going to think about the vertical succession of these facies during regression and transgression. I want to end with a brief discussion of one sequence stratigraphic surface, the regressive surface of marine erosion. This surface is uniquely developed in wave-dominated shoreface settings during the falling stage systems tract. It doesn't develop anywhere else, and so therefore it's very distinctive and diagnostic of the falling stage in a shallow marine setting. In wave-dominated coasts, the bathymetric profile, or the shape of the shoreface, is set by wave energy. There's a concave up profile in which the shore face is slightly steeper than the offshore transition or the offshore. So at the peak of the base level cycle, just before base level falls, the seafloor profile follows this dashed line here, this wave equilibrium profile. After some base level fall, base level is now at position number 2, and the new seafloor profile is the thin concave up line. So this new profile is above the previous or the initial equilibrium profile to the left of this point labeled the lever point. So that means that shoreface sediments will accumulate there in this blue wedge. But this new profile, the thin line, is below the initial dashed line offshore of the lever point, and that leads to erosion in this area. This erosional surface is called the regressive surface of marine erosion. The surface to the left of the of the lever point is called the basal surface of forced regression, but we're not going to deal with it because the basal surface of forced regression can't be recognized in outcrop. Because the facies succession is just a gradual succession or gradual shift from progradational offshore through progradational offshore transition through progradational shoreface sediments, with no obvious break or shift or change in the stacking pattern. The regressive surface of marine erosion is typically very distinctive. It normally separates finer-grained offshore facies, perhaps offshore transition facies, below from sharp-based shoreface sandstones above. The offshore transition is largely or entirely missing, so there is an abrupt grain size transition. It's potentially marked by signs of marine erosion, like gutter casts. So in this example, the offshore facies, or the facies below, likely represent the high stand systems tract prior to base level fall, and the shoreface sandstones are likely part of the falling stage systems tract. So in general, you can assume that the regressive surface of marine erosion is overlain by falling stage or FSST sediments, although that's not entirely true everywhere. The regressive surface of marine erosion can also form in carbonate environments, as shown by this example. The light gray sediments at the base of the section, or the base of the outcrop here, are outer ramp limestones, probably the HST. This irregular surface is the scoured regressive surface of marine erosion with gutter casts. And above it are darker gray inner ramp limestones with abundant Swaley Cross-Stratification, which if you look closely you can see these large scooped out swales. And this represents deposition during the falling stage systems tract again.